All right, so I wanted to show you another FRQ problem. This is another differential equations one. This is a specific type of differential equations that's called logistic. And there's a format to these, and there are some tricks that you just kind of need to know because otherwise, if you don't recognize it as a logistic and know that there are tricks, you can spend a long time trying to derive things that you just simply don't need to derive. What makes it a logistic, the second part is what makes it logistic. Okay, so let f be a function where f of 4 is equal to 1 that satisfies the differential equation dy dx equals 2y times 3 minus x. Okay, this is not a differential equation because because this is an x right there. Okay, but in the second part it says let g be a function with g of 4 equal to 1 such that all points x comma y on the graph of g satisfy the logistic differential equation 2y times 3 minus y. Okay, so that part is the differential, is the logistic one. Notice that there's no x in there. There's two y's. If you think of what's this going to be, well, it's going to be 0 at 0, and it's going to be 0 at 3. So the relevant range that we're usually going to be talking about with these is the range that's in between the two obvious zeros. Anyways, I'm getting a little ahead of myself because I said part A is not a logistic. And they don't normally do this to you, but they do in part A where they say find y is equal to f of x. And so this is your 5-point separate and integrate problem, 2y times 3 minus x. I'm going to separate it so that I just have 1 over y dy is equal to, let's call this 6 minus 2x dx. And now I'm ready to integrate. And when I integrate, I get natural log of the absolute value of y is equal to 6x minus x squared plus c. Just a note on that, y is the derivative of 1 over y, the natural log of the absolute value of y. Let's go backwards because we're usually thinking in derivatives. The function here is the natural log of x. It's only defined where y is greater than 0. So we say that the derivative of the natural log of x is 1 over x. However, 1 over x is defined in both quadrants 1 and quadrant 3. Okay, so x can be greater than 0 or x can be less than 0. So we say the antiderivative of the natural log of x is 1 over x. We say the antiderivative of 1 over x is natural log of the absolute value of x, to take into account the fact that one of those functions is only defined for the positive x numbers and one of them is defined for the negative x numbers. So that'll come back into play at the end a little bit. So now we know the point 4 comma 1, right? So this is, it's not, y hasn't been separated to be by itself, but this is more like a general solution. We're going to use this point to find the specific solution. So I'm going to put the natural log of the absolute value of 1 is equal to 6 times 4 minus 4 squared plus c. Natural log of 1 is 0. 0 is equal to 24, and c is equal to negative 8. And now I can say the natural log of the absolute value of y is equal to 6x squared minus 6x minus x squared minus 8. And then I'm going to raise e to both sides, and I'm going to call this e to the y. I'm going to drop the absolute value signs, is equal to e to the 6x minus x squared minus 8. And in the, this is just going to be y. I'm going to drop the absolute value signs. Remember, we have to keep in mind that y needs to be positive. That's what the lesson from this was. Y needs to be positive. But look at this function. Or look at the other side of this. This is e to a power. No matter what x is, no matter what the power is here, this is going to be a positive number, because if you raise a positive number to a really big number, it's positive. If you really raise something like e to a really big negative number, it's positive. So you don't have to worry much about this. That's why we say this is true for all x's. And that's kind of where the absolute value sign disappeared to. And if that part's confusing to you, I wouldn't worry about it too much. I teach this stuff and I've sort of learned what's important. And I don't feel super confident in how I understand how that absolute value on the y sign always works with the natural log of y with the antiderivative of 1 over y. And I've still managed to teach it for several years and be successful in that. So don't let that part overwhelm you. Part B is where we're switching to the logistic differential equation. So it says that g of 4 is equal to 1. Find the limit of g of x as x goes to infinity and the limit of g prime of x as x goes to infinity. Okay, so the key is recognizing that this is a logistic differential equation and knowing that logistic differential equations follow a certain pattern. And so if I show you what that pattern is, well, here's the slope field, okay? This is one particular point in the slope field, but what's going to happen if you're within this range between 0 and 3, notice if you're between 0 and 3, this part's going to be positive, this part's going to be positive. So what's going to happen, you multiply two positive numbers, you get a positive number. What is that number giving you? It's giving you the rate of change, which means if you're between 0 and 3, you're going to get a positive rate of change, which means you're going to go up, okay? As you get closer and closer to 3, this part gets closer and closer to 0, okay? So your slope, as you get closer to the top horizontal line, is going to get closer and closer to 0. If you ever got to 3, your rate of change would be 0 and you'd be stuck on that line forever. Okay, so the key is knowing that anytime you're in between the two boundaries of a logistic function, all that's going to happen is it's going to go up and it's going to flatten out and it's going to asymptotically approach whatever that top boundary is. So in this case, it's as easy as saying limit of g of x as x approaches infinity equals 3, limit of g prime of x as x approaches infinity is 0. And in part C, we're asked, for what value of y does the graph of g have a point of inflection? Find the slope of the graph at g and the point of inflection. It's not necessary to solve for g of x. Okay, so dy dx is equal to 2y times 3 minus y. I guess I would call that 6y minus 2y squared. Y prime prime is going to equal 6y prime minus 4y y prime. Or it's going to equal 6 minus 4y times y prime. And what we know about this, because we're within that range still, is that this slope is never going to equal 0. Okay, so this part will not equal 0, which means that it's only going to happen if this part is equal to 0. So 6 minus 4y is equal to 0 when y is equal to 3/2. And let's see, what is the... I just want to check what the rubric says for that one because I forget. And so they say because dy dx does not equal 0 at any point, the concavity only changes signs at y is equal to 3/2, carrying the half the carrying capacity. Okay, so the carrying capacity is that top horizontal line, which is 3. And that's the other trick with these things, is that the slope will always be maximized in between these two, as it looks on the graph. And it's true. The slope is always going to be a maximum and an inflection point in between the top horizontal line and the bottom horizontal line for any logistic equation that you get. Watch, if I change this to n minus y, I have to zoom out a little bit. Well, let's change this to 6 minus y. Four minus y. Okay, then my top boundary changed to 4. If I get rid of the 2, I think the slopes will change, but I don't think anything effectively will change within the graph. But the carrying capacity, no matter what, is always going to be halfway between the top and the bottom. The bottom is almost always going to be at 0. We're almost always going to be talking about time and some other variable that can't be negative, like population. It's almost always populations with these functions model. Okay, hopefully that's helpful.